Now that we've gone through this process once, seeing the steps that need to be taken in order to solve a system of equations using elimination, let's work through a couple more examples of this. So solve the following system of equations using elimination again. Okay, so here we go. The very first step was making sure that both equations were written in the same term order. We achieved this by making sure that both equations were written in standard form, which was ax plus by equals c. What you'll notice about both of these equations is they're already written in same term order. The x's, then the y's equal the constants. So one step done, nothing to do there. They were both already written in same term order. Second step though was to make sure that that one of the variable pairs had opposite coefficients. Okay? So let's look at that. Let's look at the x's. 4 and negative 2. They're not opposites. One's positive, one's negative, but they're two separate values. Okay? Negative 7 and 2. Again, one's positive, one's negative, but they're not the same value. However, when I look at this, I see something we could do to the bottom equation. I could multiply this negative 2 right here by a positive 2 in order to make it negative 4, which would then be an opposite of the 4 above it. So what I'm going to do in order to make one of my variable pairs have opposite coefficients is multiply this bottom equation by 2. So we still have our top equation at 4x minus 7y equals 12. But this bottom equation, distributing the 2 in, negative 2x times 2 is negative 4x. 2y times 2 is positive 4y, is equal to 2 times negative 12 is negative 24. So by doing this, you can see that our x here, the x pair, now have opposite coefficients, positive 4, negative 4. So with that achieved, having both of them in same term order and one of the pairs having opposite coefficients, I can now proceed to add the two equations together. And you can see that as we do this, the x's are going to be eliminated because they have opposite coefficients, because 4x plus negative 4x is 0. Then we have negative 7y plus 4y. That would be a negative 3y is equal to 12 plus negative 24 is negative 12. As 0 doesn't do anything, it's eliminated the x variable, so we're left with negative 3y is equal to negative 12. So solving now for y, since the x is eliminated, I divide by negative 3, divide by negative 3. This produces y is equal to positive 4. Now that we have the y solved for, we have half of what we're looking for. To find the other half, like we did in the previous example, we pick one of our equations. I'm going to take this top equation of 4x minus 7y is equal to 12. And I'm going to take this y equals 4 and plug it in for the y. So that produces 4x minus 7 times 4 is equal to 12. Simplifying the left-hand side, that's 4x minus 28. The negative 7 times 4 is negative 28 is equal to 12. Now solving for x, I'm going to add 28 to both sides. And that's 4x is equal to 40. And then I'm going to divide away the 4 from the x. And that produces x equals 40 over 4 is 10. So we already found the y, and then we use the y to find our x. We now have both the x and the y pieces of our solution. Writing this as an xy coordinate point, the solution to the system of equations is 10, 4, the coordinate point 10, 4. So if I were to graph these two equations on the same coordinate plane right here, the location at which those points would intersect each other is this point right here, 10, 4. Just by way of practice, let's go ahead and do another problem. This problem will have intricacy that we haven't seen yet, so that's the reason for this problem. So let's go ahead and now work through this next one just to get more practice. So we have negative 21x equals negative 27y plus 18. And then we have negative 6y equals 9 minus negative 9x, or minus 9x. Now, you can see right off the bat that step one, we've got some work for us. We need to write these in standard form, the ax plus by equals c. Well, to do that for the first one, I've got to get this y on the other side. So I need to add 27y to both sides. Keeping the x term first, that produces negative 21x plus 27y is equal to 18. Okay, so now that top equation is in standard form. This bottom equation, the x term is the piece that's out of place. It needs to be moved to the other side. So I am going to add 9x to both sides here. Again, keeping that x term first, that produces 9x minus 6y is equal to 9. 9x minus 6y is equal to 9. So now both of my equations are written in standard form, which means my x's are lined up, my y's are lined up, and my constants are lined up. The next thing we need to do is make sure that one of the pairs, one of the variable pairs, have opposite coefficients. So let's look at negative 21 and 9. Definitely not opposites. Look at 27 and negative 6. Definitely not opposites. And the other problem here is that 9 does not go into 21, so I can't just multiply 9 by something, and 6 does not go into 27, so I can't just multiply 6 by something. So we've got some issues to solve here. What we have to do here is we're going to actually have to multiply both equations by something. To do that, what we're going to do is we're going to take a look at one of the pairs and find the least common multiple. Okay, least common multiple. Now, by looking at this really quick, I'm noticing something about the y's. I'm looking at the 27 and 6 here. And looking at that 27 and 6, the least common multiple of 27 and 6, I believe, is 54. You multiply 27 by 2 to get 54. You multiply 6 by 9 to get 54. Both 27 and 6 go into 54. So that's the number that we're going to try to achieve in front of our y values, because it's the least common multiple of the coefficients that are in front of them right now. Okay, so how do we turn 27 into 54? We multiply by 2. So this top equation is going to get multiplied by 2. Multiplying that in, 2 times negative 21x is negative 42x. 2 times 27y is positive 54y, is equal to 2 times 18 is 36. So that's the top equation. Now this bottom equation, how do I turn 6 into 54? Well, I have to multiply by 9 in order to get that. Okay, so with that, let's multiply 9 into both equations. Oh, give me one moment. Let's multiply 9 by both equations, or multiply the bottom equation by 9. So 9 into 9x becomes 81x. 9 into negative 6y becomes negative 54y. And 9 into 9 becomes 81. So now we've achieved a situation in which we have a system of equations where everything is in the same term order, x's, then y's, then constants, and my y's now have opposite coefficients, positive 54 and negative 54. This is the point at which I now add the equations together. So negative 42x plus 81x gives us 39x. Okay. And then 54y plus negative 54y gives us nothing. They cancel out, they go away, is equal to 36 plus 81 being 117. So we have 39x is equal to 117. Good. So we now have the equation 39x equals 117 that we can solve for x because the y has been eliminated. To do that, I'm going to divide by 39, both sides. So that's x is equal to, let's see, 117 divided by 39, I believe is 3. So x is equal to 3. X is equal to 3. Great. So we have half of our system of equations solved now. Well, to find the other half, I've got to take what I just solved for x, plug it into one of my equations, and solve for y. I'm going to keep it easy on myself. I can pick any of the equations in my system at any stage in the manipulation. I'm going to go back to the original problem here, and I'm going to select the negative 6y is equal to 9 minus 9x. And I'm going to plug this x into the x in this equation. So that's negative 6y is equal to 9 minus 9 times 3. So simplifying that on the right-hand side, that's negative 6y is equal to 9 minus 27. Negative 9 times 3 is negative 27. So negative 6y is equal to 9 minus 27 is negative 18. Finishing off solving for y, I do that by dividing away negative 6 from the y. Do that to both sides, and that produces y equals 3. And there we go. We now have our y value. So we first solved for x by eliminating the y. We found that x was 3. We plugged that back into our equation, into one of the equations, and we found that our y value was also 3. So the coordinate point that is the solution to this system of equations is the point 3, 3. So again, to put that in context, this is the only coordinate point that will work in the original equations. Okay? If we were to graph these linear equations in our system, the point at which they would intersect is the point 3, 3. So solving by elimination involves eliminating one of the variables first so that we can solve for one of the variables. Once we have that, it's a matter of substituting that value in to one of the original equations and solving for the other variable.